Okay, you have definitely seen this chart hanging in just about every science classroom on the planet. It's the periodic table. And you know what? It is so much more than just a list of elements. It's actually one of the most powerful predictive tools ever created. So, let's decode this thing.
At first glance, I know, it might just look like a colorful grid of boxes. But what you're looking at is basically a map of the entire known universe. It's a cheat sheet for all of matter. This table brilliantly organizes all 118 known chemical elements that make up, well, everything.
And that's the big question, isn't it? It looks super complex, but once you get the logic behind its layout, it's this incredibly elegant and, frankly, beautiful tool. So how do we unlock its secrets? How do we learn to read the map?
All right, here's our game plan. We're going to start with the most basic unit on the map, the element itself. Then we'll figure out what the rows and columns are all about. After that, we'll uncover the secret of its chemical families, and finally, we'll get into the amazing story of the guy who saw the whole pattern before anyone else.
Okay, first things first. Before we can even begin to understand the map, we have to understand what it's mapping. So let's zoom all the way in on a single point, the element. So everything, and I mean everything, is made of atoms. And every atom has a core, which we call the nucleus. Inside that nucleus, you've got positively charged protons and neutral neutrons. And then, whizzing around that nucleus, you have these tiny negatively charged electrons. These three little particles are the building blocks for the whole shebang. A chemical element, then, is really just a pure substance where every single atom is the exact same type. So, a chunk of pure gold, it only contains gold atoms. A breath of pure oxygen? You guessed it, only oxygen atoms. The real question is, what makes a gold atom different from an oxygen atom?
Well, it all comes down to one single thing: the number of protons in the nucleus. That's it. That is the unique ID for every single element. Hydrogen has 1 proton. Helium has 2. Lithium has 3. This is the element's atomic number, and it is the single most important organizing principle of the entire table. It's how every element gets its spot.
So, now that we know what an element is and how it gets its identity, let's look at the table's structure. You see, it's organized into these horizontal rows and vertical columns, and each one of them tells us something totally different and really important.
The horizontal rows are called periods. I want you to think of an atom kind of like an onion. Every element in the same row has the same number of layers, or what we call electron shells. But the vertical columns, those are called groups. And this, my friends, is where the magic happens. Elements in the same group have similar chemical personalities, and that's because they have the same number of electrons in their outermost layer.
And honestly, understanding the groups is the real secret to reading this table. This is how you avoid having to memorize 118 different elements. Instead, you just learn the characteristics of a few key groups, or chemical families. Let's check out 2 totally opposite examples.
Let's start all the way over on the right side of the table with group 18. These are the noble gases. You've probably heard of some of them, right? Like the helium that makes balloons float, or the neon in those cool, glowing signs.
The defining feature of the noble gases is that they're, well, kind of standoffish. They are super stable, and they really don't like to react with other elements. And why is that? It's because their outermost electron shell is completely full. They're happy. They don't need to gain or lose any electrons, so they just keep to themselves.
Okay, now for a complete contrast, let's jump all the way over to the far left side. Group 1, the alkali metals. These elements are the total polar opposite of the noble gases.
The alkali metals, think lithium and sodium, are incredibly reactive. They desperately want to interact with other elements. And the reason is simple. They have just one lonely electron in their outer shell. It's way easier for them to just give that one electron away to become stable. And it's this desire that makes them so reactive, a property we actually use in things like lithium-ion batteries.
You know, this elegant system that predicts how elements will behave. It feels almost obvious to us now, but it wasn't always this way. To see how it all came together, we really need to look at the work of one particularly brilliant scientist.
For decades, scientists had been trying to organize the elements. People like Lavoisier grouped them into basic categories. Others noticed that properties seemed to repeat when elements were arranged by their weight. But it was the Russian chemist Dmitry Mendeleev in 1869 who had the crucial, game-changing insight. See, Mendeleev also organized his table by atomic weight, but, and this is the key, he was so confident in the patterns he saw that when an element didn't fit, he didn't try to force it. He just left a blank space, predicting that a new element would one day be discovered to fill that gap. And guess what? He was right.
He even predicted the properties of these missing elements with just stunning accuracy. So, in the end, the periodic table isn't just some reference chart. It is a testament to the fundamental order of the universe. It proves that the properties of matter aren't random at all. They follow this beautiful, predictable pattern, all based on something as simple as counting protons and arranging electrons.
It really is a map of matter, one that has guided scientists for over 150 years and still does today. It makes you wonder, doesn't it? If something as fundamental as all the stuff we can see and touch follows such a clear, logical pattern, what other elegant secrets are just out there waiting for us to decode?